If I asked you, the Mulukis, to draw what KK would look like in the future. If you're an optimist, you might draw something like this. A futuristic city, lots of green areas, flying cars, etc. If you're a pessimist, you might draw something like this. If you're a realist, you'd probably draw that. Okay? That we probably won't see significant changes. So this module is trying to talk about how climate projections are made. We don't know what the future's going to be. No one can tell you definitely how much warming we're going to have. Okay? And so we need to use climate models to project what the range of possible futures are. Are we going to be in a utopia? Are we going to be in a Blade Runner type universe? Okay. I need to ask you, do you know the difference between weather and climate? Okay, weather, if you go out there now, you will experience weather. Okay, it's what you feel in terms of temperatures, winds and rain. Climate is slightly different. Climate is the long-term pattern of weather. And typically, it's the average weather condition over at least a 30-year period. Okay, so when we're talking about climate, we're talking about the averages for a 30-year period. Climate models make projections of future climates. They're not projections of future weather. So a climate model cannot tell you that on your birthday in 2030, it's going to rain. What it can tell you is that in 2050, the period between 2050 and 2080, it's going to potentially probably be X degrees warmer, depending on what scenario. In our work, we use 3 climatologies. Please don't shift. A baseline from 1981 to 2010, a mid-century one, 2041 to 2070, and an end-of-century one, 2071 to 2000. Different studies use different baselines, and they also sometimes use different future projected periods. For today's presentation, the next presentation, I'll be limiting it to the end of century relative to this baseline, okay? So when I talk about something relative to the baseline, I'm talking about the climate that was experienced 1981 to 2010 compared to what we'll be looking in the future. So how are climate projections made? Well, the fundamental tool of any climate projection work are the general circulation models or Earth system models. And these are mathematical representations of our atmosphere, our oceans, our terrestrial bits, and also the cryosphere, which is the frozen bits, your ice caps, your glaciers. And in a climate model, it models the fluxes of mass, energy, and carbon between these systems in grid cells. So energy transferred between grid cells, across grid cells, etc. Climate models were developed and calibrated using the historic data. Okay? And then what we do is we develop the model and then you project it over your future. Climate models have not been static. So this graph is taken from the Assessment Report 5, shows the evolution of climate modeling. Zaman dulu, the climate models were very simple. The number of bars, number of rows, represents the number of systems in the model. The width of the column, or the height of the column, represents how many processes were being modeled at the time. So, early models were very, very simple. They did atmosphere, land surface area, and ocean and sea ice. And you see there weren't many processes included in them. Then slowly over time, they expanded what was being incorporated in the model to include aerosols, carbon cycles, vegetation dynamics, atmosphere chemistry, and land ice. And you can see also over time the number of processes in each of these parts has increased. So the point is, the models are continuously evolving. As soon as our science improves, the model is updated. So if we start to have a better understanding about how El Nino are going to be impacted by climate change, that will be put in the model. Another thing is the performance is always being assessed. Okay? Climate models are being checked on how accurate their predictions are. And if anyone wants to look at some of these papers, this one here is a paper from a couple of years ago, which looked at how well the CIMP, that one, third assessment report, fifth assessment report, and the one that's just been released, actually perform in predicting observed temperatures. And the depressing bit is the climate models have been a little bit conservative. We're seeing observed temperatures higher than we predicted, even under the worst case scenario, the 8.5 relative forcing. There's also evaluations on how well they perform in rainfall. Rainfall is a bit of a mess. Some models do good, some models do bad, but the projections are a lot less definite than the temperature. So this is a climate model. Yep. It is, you've got your GCMs or Earth system models. There are in excess of 37 of them. I don't know the exact total. I can get access to data to about 37, but there's others out there where we can't. And these are the governing equations. Okay, next. You then have your initial starting conditions, and this is data based on the data from weather stations. So real data that's been collected by Meteorological Department of Malaysia and everyone else. It goes into a global data set. We then have the future conditions, and this is that relative forcing, okay? And what they have, because no one knows what the future is going to hold, they have created a range of possible scenarios. Part of the confusing thing is that the scenarios' names change under every single report. Okay, so previously we were talking about RCPs, now we're talking about SSPs, and next year I don't know what we'll be doing, okay? They'll probably have changed again. But they're just scenarios of what might happen. So just to recap relative forcings, you remember the relative forcing is the difference between how much energy was being retained pre-industrial in 1750 versus how much is being retained by increases in greenhouse gases. Okay, the more GHGs in the atmosphere, the more GHGs that we release, the higher the relative forcing. So that's what you just got to remember. The number that is higher means it's going to be hotter. The higher the RF becomes, the hotter it is, okay? These are the relative forcings that are being used by the IPC scientists currently, okay? Ranging from 1.9, which is a relative forcing of 1.9, which corresponds to about a 1.5, 1.4 degree rise in temperatures. RCP, or relative forcing 4.5, which is our trajectory now, which corresponds to roughly about a 2.7. And then there's 7.0 and 8.5. In the last IPCC report, sorry, the previous one before AR6, the scenarios were just called RCP, representative concentration pathway, and then they would just number the relative forcing. Okay, so RCP 6 referred to a 2.6 watt per meter squared relative forcing. Okay, RCP 8.5 was the 8.5 watts per meter squared. Okay, this was easy for me to understand. They've complicated the scenarios a bit because what they've added onto it is something called a shared socio-economic pathways. So rather than just talking about the greenhouse gases and their impact, they're also bringing in how different alternative development pathways, SSP 1, 2, 3, 4, and 5. Okay. And what I think we have next is a visual representation to try to explain what an SSP is. Okay, so these is not about how much greenhouse gas is being emitted. It is in a shared socioeconomic pathways, there are projections on the level of economic development, on populations, increases in populations. There's projections on how we're going to get on. Are this nation going to try and beat up that nation? There's also projections on how we're going to deal with people in our own society. Okay, so SSP2 is our current, what we're doing now. Some countries have got a lot of social inclusion, a lot of equity. Others are, you've got a massive separation between rich and poor. Some countries get on with each other, others are fighting. Okay, so this is the middle of the road. This one, rich nations, small population growth, poor nations, high population growth. SSP1 is where we choose a sustainable future, a green pathway. We reduce our own consumption. Okay, so the average Australian doesn't eat however many kilograms of beef a year. We reduce meat consumption. We also decrease our population growth globally. We become more equitable. We have less distinction between rich and poor. We also all become friends. We stop trying to kill each other and have wars. Okay? So this is a pathway where everything becomes good, and it's driven largely by green development. Okay. SSP5 is in some ways a little bit similar. We all become no longer killing each other, where consumption increases, that's one of the differences. Population is low, but development is all fossil fuel driven. So basically it is all burn, baby, burn. Sabah goes and exploits its coal mines, but we use that money from the coal mines, instead of Masuk Pocket YB, we use it to bring up our B40s, okay? So we use it to create a society which is a little bit more equal, okay? So people here, sure, there's more greenhouse gases and etc., but they're going to have more ability to adapt, okay? These scenarios here, SSP3 and SSP4. SSP3 is where we separate into a Western bloc, maybe a non-aligned bloc, and other bloc, and we start to no longer cooperate. We don't work together on solving the problems. We start killing each other, etc. SSP4 is where the separation is within one society. So instead of bringing our B40s up financially, what we do here is the rich get richer, the poor get poorer, population growth in poor countries increases, the people in rich countries stay rich, and we close our borders, etc. Okay? So these are the bad case scenarios. And what they've done is they've then coupled it with, can we go back to the last slide? Coupled it with some of the representation, some of the relative forcings. So SSP1 can occur with relative forcing of 1.9 and 2.9. Middle of the road is coupled with the one that we practice. The regional rivalry has a higher relative forcing. And then this one, I know nothing about because I haven't been able to get any data for it. And then this is one where we have a really high greenhouse gas emission, but we have a society which is slightly better than in these ones, okay? For our work, we've only managed to get data for SSP 126, 245, 370, and 585. And when we will refer to things, you'll often hear us just say 245, okay? Just remember that's the middle of the road path with a relative forcing of 4.5, okay? Okay, so you've got your model, your ESM, GCM, you've got your forcing condition, you have the various ones you want to play with, you've got your initial conditions, you whack it in, you wait however many days, I don't know, I don't do this, and it puts out output. If anyone wants to get the output, these hyperlinks link you to the data sets. So part of our transparency process on this work is all of the data sets that I talk about and all of the scientific papers that we refer to are hyperlinked in the document, so you can go and check yourself, although we've done a lot of the cleaning work. The model puts out rainfall, temperature, air pressure, wind speed, soil moisture, okay? Massive amounts of information, about 5 terabytes for one run, okay? And it looks like this. I'm sorry, it's America. It's because this was the only site that I could get that actually shows the grid cell size from a GCM, okay? So you see these blocks. This is a grid cell. And where they're doing the modeling, because they're doing global modeling about this massive complex, information, they do it at a grid cell of somewhere between about 1 and 3 degrees. And that translates somewhere between 100 and something to 350 kilometers, okay? So they're quite big areas, okay? This is not of sufficient spatial resolution to say anything about what happens in Sabah. Why? Because Sabah would be that. It would be a single grid cell, depending on the model. Some models you might get 2, okay? So what we need is downscaled data. Okay, next click. And this is an example of where they've taken the data and they've downscaled it. So they've taken something which was at 300 kilometer resolution, and this model is now at 25 kilometer resolution. And this is the resolution where you can start to work on. Okay, next slide. So what downscaling is, global grids, you focus into a local area, you have to have information about the local area. So you need data, rainfall data, you need temperature data, you need elevation models to be able to do your downscaling. There are 2 different methods. One is a statistical downscaling method, which is the one we tend to get the data from the most. The other way is called a dynamic downscaling method, which uses something called a regional climate model. Okay, the reason why most people do statistical is because it's a lot less time consuming in terms of computing time. NASA has downscaled all of the GCMs, all of the projections for 35 GCMs, uploaded it onto a site, free data, whereas data from us, regional climate models, there's only a handful of it available, okay? Next slide. So again, I need to stress, we are not doing the modeling. The data that we're using is coming from these guys, the World Climate Research Program, which is part of the World Meteorological Organization, okay? They're the climate scientists with the big brains that develop these general circulation models that produce that first map, that big blocky one, okay? Then certain organizations are incredibly nice. This is WSL, is the Swiss Federal Institute for Snow, Forests and Ice, and they've gone and done the statistical downscaling for us. They've taken the projections from here and then downscaled it, temperature, both maximum, mean, minimum, mean, rainfall and relative humidity, and they produced it as mean monthly values for a 30-year climatology. So you'll get an estimate, a projection for January, February, March, April, May for the years 2041 to 2070. So it's averaged over those 30 years. It's at 1 kilometre resolution, so quite very fine resolution. We've only taken 5 of the general circulation models and have got it for the 4 shared socioeconomic pathways. NASA has done something similar, but what they did, so temperatures, max, min, relative rainfall, relative humidity, is they've downscaled it, the daily projections. So instead of a monthly one, they have a daily projection. So if you go into their files, it's a TIFF file. So for anyone that's a GIS head, it's like a map. And in that map, there are 350 to 366 layers, okay? And each of those is a projection for that year of what the rainfall or temperature will be for that grid cell, okay? Their projections range from, it's 1950 or something, or 1955, up to 2100. It's at a less spatially resolved. It's at 25 kilometers rather than 1. And we've also got it for 5 GCMs, exactly the same GCMs and the 4 SSPs. And this is the data set that we're using for terrestrial work. We've also been scavenging as much as we can for the marine environment. And we got a paper from data set from University of Plymouth of the physical chemical variables. They have 29 variables, but so far we've only processed the sea surface temperatures, the pH and dissolved oxygen. They've also taken their data, they use a regional climate model, and they put the data into what a fisheries model, and then they calculate or they project what will happen to fish stocks. And they've done that for 80 commercially important fish in the Southeast Asian region, of which about 50 are important for Sabah. And they have yearly projections, 11 kilometre resolution, so the grid cells, the pixels, are 11 kilometres square from historic to the end of the century. And then we also collected information on sea level rise and storm surge. It's 11 kilometre resolutions. It's from 4 general circulation models. It's only for the period 2021 to 2050. And it's got storm events of different return periods. So a once in 1 year storm is, as it says, a storm that will occur once in 1 year. So it's a moderate storm. A once in 100 year storm is one that you only get within maybe your lifetime, once in your lifetime or maybe less. So it's a Turuk storm, okay? And what it means is these are really strong storms and the storm surge will be sangat tinggi, okay? Is we take the different projections and then we create what's an assembled model. Okay, just go through that. Okay, because what you want when you're doing this, the modeling work, and you're looking at the impacts, is you don't base your results where possible on a single model, because models vary in their projections, and some models do better in certain areas, some models are rubbish, and some models are probably better than average. Okay, and so what you do is you collect what you can in different models, you collect their projections, and then you sum it all, or you mean it all up to say this is the likely impact in Sabah. Okay, next. So this is some of the data. This is mean maximum temperature. It's from that first set of data, the WSL or Chelsea data, and it shows current. We have a mean maximum temperature for the warmest month of about 32.65 degrees. End of century, it's increased by about 1.2 degrees on a low emission scenario. On our current trajectory, it increases to about 34.85 degrees. On the high emission scenario, it goes up to 35.45 degrees. Okay, so this is what temperature will look like. But if we showed anyone this map, can you push the next? The question would be so what? What does 35.45 degree mean maximum temperature mean? I mean, Australia, we get up to 40 degrees. Yeah, we have months where your mean maximum's something, in the 40s, okay? So temperature by itself may not be the most informative bit of information. So what we do is we take all of this information and then try to look at how these changes are going to impact things in Sabah. Okay, we know that temperature increase is going to impact our health, heat stroke and health. And it's not just temperature alone, temperature combined with relative humidity. That's the killer. So what we produce are heat stress indices, or wet bulb globe temperature projections, which combined these two variables to look at what might happen. We've also looked at how it might impact different workers. You can have a temperature of the heat stress index, and then you can get, based on what type of work they're doing, you can work out how many hours they're going to lose, okay, of work. You can also, if you really want to do, you can look at how much sleep you're going to lose under warmer conditions, and how worse your students are going to go in their exams. Okay, there's science which basically allows you to say the PISA scores decrease by X for every degree warming. And we also go and look at how this will affect our agricultural system. So there are temperature heat indices for livestock, different ones for different livestock. And that allows you to look at how it might impact growth and mortality of our livestock. There is work out there, some done by Malaysian researchers, that look at how temperature impacts rubber yields. There's global work on rice, worker productivity, walker balance, also ecosystems. We're modelling fire risk, we're modelling water balance, and there's also other ways you can look at it, okay? And all it is doing is taking the information that comes from the IPCC scientists, has been downscaled by those very nice organisations, and then taking the research that has been done, some of it by Malaysian researchers, to produce a map that shows how much more electricity we're going to need in Sabah. Because increased temperatures, there'll be this much potential increased electricity demand. Okay, next slide. Oops. Okay, so that was temperature. And it's really easy when you're doing this work just to think about a single variable, okay? And go, it's only temperature we have to worry about. but it's not. When you're looking at climate change impacts in Sabah and trying to explain them, it's not just temperature that's going to be impacted. We'll have increased temperatures. The hotter it is, the more moisture the atmosphere can retain. And this means that relative humidities are projected to also potentially increase. More water in the atmosphere and also changes in airflows are going to result in changes in rainfall patterns. Okay. The hotter temperatures are going to cause thermal expansion of water, as well as the melting of your glaciers and your Arctic, your Greenland and Antarctic ice caps. Again, rising water levels, sea level levels. And the temperature's going to change factors in the oceans. You're going to have increased sea surface temperatures. You're going to have reduced dissolved oxygens. On top of that, this carbon dioxide that we're releasing, the more carbon dioxide leads to an increase in the acidification of the ocean. So when we're trying to look at how Sabah will be impacted by climate change, we can't just go focus on that. You also have to start to think about all of these and how it will impact. Okay? So in the next module, what we will be doing is we will be going through, can you go back 2 slides? No, next. Some of our findings on how the various variables are likely to impact Sabah in terms of agricultural yield, agricultural yields, rice in particular. We'll be looking at how fire risk is likely to change in Sabah. We'll be looking at some indications of how heat is going to impact particularly rural communities. Okay, so that's it for this session.